In the quiet hours of your evening, as the familiar world settles into darkness around you, there exists a theory so profound and disturbing that it challenges every assumption you've ever held about the nature of existence itself. Tonight, we're going to explore a corner of physics where reality fractures into infinite possibilities, where the very act of observation creates the universe, and where the boundary between what is real and what is possible dissolves entirely. Let the day's concerns fade away. Forget about time itself. There's nowhere urgent you need to be, nothing pressing demanding your immediate attention. For the next few hours, we'll journey together through the most mind-bending implications of quantum mechanics, following a trail of evidence that leads to conclusions so extraordinary that even the scientists who discovered them struggled to accept what they had found. The theory we're about to examine doesn't just challenge physics, it challenges the fundamental nature of reality, consciousness, and existence itself. It suggests that the universe you experience is just one of an infinite number of parallel realities, that your consciousness might be the force that collapses possibilities into actuality, and that everything you consider real might be nothing more than a fleeting arrangement of probabilities. This isn't science fiction. This is the cutting edge of scientific understanding, where the most brilliant minds of our species have ventured into territory so strange that it makes Alice's Wonderland seem mundane by comparison. Let's begin this unhurried exploration at the moment when physics took its most bewildering turn, in the early decades of the 20th century, when a handful of European scientists stumbled upon discoveries that would fundamentally alter humanity's understanding of existence itself. The story begins, as many revolutionary discoveries do, with an anomaly that refused to behave according to the established rules. In 1900, Max Planck was attempting to solve what seemed like a straightforward problem in physics, explaining the spectrum of light emitted by heated objects. The existing theories predicted that such objects should emit infinite amounts of energy at high frequencies, a prediction so absurd that physicists called it the ultraviolet catastrophe. Planck's solution was elegant but deeply troubling. He proposed that energy couldn't be emitted continuously, as everyone assumed, but only in discrete packets he called quanta. This was like suggesting that you could only climb a staircase by jumping entire steps, never landing between them. The idea worked mathematically, solving the ultraviolet catastrophe with remarkable precision, but it violated every intuition about how the world should operate. Planck himself was deeply uncomfortable with his discovery. He spent years trying to find a way to explain his quantum hypothesis using classical physics, unable to accept that he had uncovered something genuinely new about the fundamental structure of reality. He never succeeded in this effort, and eventually he grudgingly accepted that nature operated according to principles that defied common sense. But Planck's quantum was just the first crack in the edifice of classical physics. In 1905, Albert Einstein expanded on Planck's work by proposing that light itself came in discrete packets, photons. This explained the photoelectric effect, a phenomenon where light striking certain materials would eject electrons, but only if the light exceeded a specific frequency threshold. No amount of low-frequency light, no matter how intense, could produce the effect, while even dim high-frequency light would work immediately. Einstein's photon theory was revolutionary because it suggested that light, which had been understood as a wave for over a century, also behaved like a particle. This wave-particle duality was the first hint that the quantum world operated according to principles that were fundamentally different from everyday experience. The implications were staggering. If light could be both wave and particle, what did this mean for the nature of reality itself? The question would haunt physics for decades, leading to discoveries that would challenge every assumption about the nature of existence. Niels Bohr took the next crucial step in 1913 when he applied quantum principles to the structure of atoms. The classical model of the atom, with electrons orbiting the nucleus like planets around the sun, had a fatal flaw. orbiting electrons should continuously radiate energy and spiral into the nucleus within fractions of a second. Atoms should be impossible, yet they obviously existed. Bohr proposed that electrons could only occupy specific energy levels, or orbits, around the nucleus. They could jump between these levels instantly, absorbing or emitting photons in the process, but they could never exist between the allowed levels. This quantum model of the atom explained the stability of matter, but it introduced a new paradox. Electrons seemed to teleport from one orbit to another, without traveling through the space in between. The Bohr model worked brilliantly for hydrogen, accurately predicting the wavelengths of light emitted by excited hydrogen atoms. But as physicists tried to extend it to more complex atoms, they encountered increasingly strange phenomena that classical thinking couldn't explain. Werner Heisenberg, working in the 1920s, made the next breakthrough by abandoning any attempt to visualize what was happening inside atoms. Instead, he focused purely on what could be measured and observed, developing a mathematical framework that could predict the outcomes of experiments without requiring any mental picture of underlying reality. Heisenberg's approach was radically abstract. His equations dealt with matrices of numbers that corresponded to observable quantities, but they didn't describe any physical process that could be visualized or understood in everyday terms. It was as if he had discovered that nature's fundamental language was pure mathematics, divorced from any underlying physical reality. This mathematical formalism worked with unprecedented accuracy, but it came with a disturbing implication. Heisenberg discovered that certain pairs of properties, such as the position and momentum of a particle, could not be measured simultaneously with perfect precision. The more accurately you determined one, the more uncertain the other became. This wasn't a limitation of measurement instruments. It was a fundamental property of reality itself. The Heisenberg uncertainty principle suggested that particles didn't have definite positions and momenta simultaneously. Instead, they existed in a state of fundamental uncertainty, with properties that became real only when measured. The act of measurement itself seemed to play a crucial role in determining what became real. Around the same time, Erwin Schrödinger was developing a different approach to quantum mechanics. His wave equation described particles as wave-like probability distributions that extended throughout space. These probability waves could interfere with each other, creating patterns of high and low probability for finding particles in different locations. Schrödinger's equation was elegant and powerful, capable of predicting the behavior of quantum systems with extraordinary precision. But it raised profound questions about the nature of reality. If particles were described by probability waves, what did this mean about their actual existence? Were particles real physical objects, or were they merely statistical abstractions? The question became acute when considering what happened during measurement. Before measurement, Schrödinger's equation described particles as existing in superposition, simultaneously occupying multiple states or locations. But when a measurement was performed, this superposition would collapse into a definite state. This collapse seemed to happen instantaneously, regardless of how spread out the probability wave had been. If an electron's wave function extended across a room, measuring it at one location would instantly eliminate the probability of finding it anywhere else. This suggested that information could travel faster than light, violating one of the fundamental principles of relativity. Schrödinger himself was troubled by these implications. To illustrate the absurdity of applying quantum mechanics to everyday objects, he devised his famous thought experiment involving a cat in a box. According to quantum mechanics, if the cat's fate depended on a quantum event, the cat would exist in a superposition of being both alive and dead until someone opened the box to check. Schrödinger intended this as a reductio ad absurdum, demonstrating that quantum mechanics must be incomplete. Surely cats couldn't actually be both alive and dead simultaneously, yet the mathematics of quantum mechanics insisted that this was exactly what should happen. The debate over the meaning of quantum mechanics intensified throughout the 1920s. Einstein, despite his contributions to quantum theory, became increasingly uncomfortable with its implications. He famously declared that God does not play dice with the universe, expressing his conviction that there must be some underlying deterministic reality beneath the apparent randomness of quantum phenomena. Einstein believed that quantum mechanics was incomplete, that there must be hidden variables that determined the outcomes of quantum measurements in ways that appeared random only because we couldn't access this hidden information. He spent much of his later career searching for a more complete theory that would restore determinism to physics. Bohr, by contrast, embraced the radical implications of quantum mechanics. He argued that the wave-particle duality wasn't a limitation of our understanding, but a fundamental feature of reality. Particles weren't really waves or particles in the classical sense. They were quantum objects that exhibited different aspects depending on how they were observed. Bohr's principle of complementarity suggested that classical concepts like wave and particle were inadequate to describe quantum reality. The properties we observed depended on the experimental setup we used to observe them. In some experiments, quantum objects behaved like particles. In others, they behaved like waves. Both descriptions were necessary but incomplete. This philosophical position, known as the Copenhagen interpretation, became the orthodox view of quantum mechanics. It suggested that quantum mechanics was complete as it stood, and that the strange phenomena it predicted, superposition, uncertainty, wave-particle duality, were genuine features of reality rather than limitations of our knowledge. But the Copenhagen interpretation came with a troubling implication. It suggested that reality itself was fundamentally observer-dependent. The act of measurement didn't just reveal pre-existing properties, it actually created those properties. Before measurement, particles existed in indefinite states of superposition. The measurement process somehow selected one possibility from many, collapsing the wave function into a definite outcome. This raised profound questions about the role of consciousness in physics. What constituted a measurement? Did it require a conscious observer, or could any physical interaction cause wave function collapse? If consciousness was necessary, this suggested that mind played a fundamental role in determining physical reality. These questions became more urgent as physicists developed increasingly sophisticated experiments to test the predictions of quantum mechanics. In the 1930s, Einstein and his collaborators Boris Podolsky and Nathan Rosen devised a thought experiment designed to demonstrate that quantum mechanics must be incomplete. The EPR paradox, as it became known, considered two particles that had interacted and then separated by large distances. According to quantum mechanics, these particles would remain entangled. Measuring one would instantly affect the other, regardless of the distance between them. Einstein argued that this spooky action at a distance was impossible, and therefore quantum mechanics must be incomplete. Either information was traveling faster than light, which violated relativity, or the particles must have predetermined properties that quantum mechanics failed to account for. Einstein preferred the second option, arguing for the existence of hidden variables that would restore locality and determinism to physics. For decades, the EPR paradox remained a philosophical puzzle rather than an experimental question. The technology didn't exist to test whether entangled particles actually exhibited the correlations that quantum mechanics predicted. But in the 1960s, physicist John Bell developed a mathematical framework that could distinguish between quantum mechanics and hidden variable theories. Bell's theorem showed that any local hidden variable theory would make predictions that differed from quantum mechanics in specific, measurable ways. If quantum mechanics was correct, certain correlations between entangled particles would be stronger than any local hidden variable theory could explain. Bell's work transformed a philosophical debate into an experimental question. Beginning in the 1970s, a series of increasingly sophisticated experiments tested Bell's inequalities. The results consistently supported quantum mechanics and ruled out local hidden variable theories. Alain Aspect's experiments in the early 1980s provided particularly compelling evidence. Using entangled photons separated by large distances, Aspect showed that the correlations between their properties violated Bell's inequalities, in exactly the way that quantum mechanics predicted. The experiments seemed to confirm that quantum entanglement was real, that measuring one particle really did instantly affect its distant partner. These results had profound implications for our understanding of reality. They suggested that the world was not locally real in the way that classical physics assumed. Either locality was violated, information could travel faster than light, or realism was violated. Particles didn't have definite properties independent of measurement. Most physicists accepted the violation of realism, concluding that quantum mechanics accurately described a world where properties became real only through measurement. But this raised even deeper questions about the nature of reality and consciousness. If particles didn't have definite properties until measured, what constituted a measurement? The quantum measurement problem became one of the most challenging issues in physics. When exactly did the wave function collapse? What distinguished a measurement from any other physical interaction? Some physicists, following the Copenhagen interpretation, argued that collapse occurred when the quantum system interacted with a classical measuring apparatus. But this raised the question of what made something classical. Where was the boundary between the quantum and classical worlds? Others suggested that consciousness itself was responsible for wave function collapse. This interpretation, associated with physicists like John von Neumann and Eugene Wigner, proposed that measurement occurred only when a conscious observer became aware of the result. Before consciousness intervened, systems remained in superposition indefinitely. This consciousness-based interpretation had startling implications. It suggested that consciousness wasn't just passive observer of reality, but an active participant in its creation. The universe would exist in a state of indefinite possibility until conscious minds collapsed the wave function through the act of observation. But the consciousness interpretation faced serious problems. It seemed to give human consciousness a special role in physics, contradicting the principle that physical laws should be universal. It also raised questions about animal consciousness and the evolution of the universe before conscious beings existed. An alternative interpretation emerged in the 1950s when Hugh Everett III proposed his many worlds theory. Everett suggested that wave function collapse never actually occurred. Instead, all possible outcomes of quantum measurements were real, but they existed in parallel universes that couldn't interact with each other. In Everett's interpretation, Schrödinger's cat was both alive and dead, but in separate universes. When you opened the box, you didn't cause the wave function to collapse. Instead, you became entangled with the quantum system, splitting into two versions of yourself. One version found a live cat, the other found a dead cat, and both versions were equally real. The many worlds interpretation eliminated the need for wave function collapse and preserved the deterministic evolution of the universal wave function. But it came at an enormous cost. It required believing in the existence of an infinite number of parallel universes, constantly branching as quantum measurements occurred throughout the cosmos. According to many worlds, every quantum event splits the universe into multiple branches. The universe containing your current experience is just one of countless parallel realities where different versions of you made different observations and experienced different outcomes. This interpretation suggested that every possible history was equally real. Somewhere in the multiverse, Napoleon won at Waterloo. Dinosaurs never went extinct, and you made different choices at every moment of your life. All of these possibilities existed in parallel, separated only by the quantum branching events that differentiated one universe from another. The many worlds interpretation gained support from some physicists because it eliminated the problematic aspects of wave function collapse while preserving the mathematical structure of quantum mechanics. It also provided a framework for understanding quantum cosmology, the application of quantum mechanics to the universe as a whole. But many worlds faced its own philosophical challenges. If all possible outcomes were equally real, what made your particular branch of reality special? Why did you experience this particular sequence of events rather than any other? The theory seemed to drain the concept of probability of any meaningful content. If all outcomes occurred, what did it mean to say that some were more likely than others? Despite these interpretational debates, quantum mechanics continued to produce technological marvels. The theory that seemed to challenge the very nature of reality also enabled the development of lasers, transistors, computer chips, and magnetic resonance imaging. The strange quantum properties that philosophers found so troubling proved to be the foundation for much of modern technology. The success of quantum technology added urgency to understanding what the theory really meant. If quantum mechanics could be used to build practical devices, then its weird predictions about superposition and entanglement must be describing something real about the world, not just mathematical abstractions. In the 1980s and 1990s, physicists began to explore the practical applications of quantum strangeness itself. Quantum cryptography used the no-cloning theorem, the impossibility of perfectly copying an unknown quantum state, to create unbreakable codes. Quantum computing proposed to harness superposition and entanglement to perform calculations that would be impossible for classical computers. These developments made the interpretation of quantum mechanics more than just a philosophical curiosity. If quantum computers could factor large numbers exponentially faster than classical computers, as theorists predicted, then the superposition of quantum states must be doing real computational work. The question of what quantum mechanics meant became urgent for understanding what these machines were actually doing. The field of quantum information theory emerged to study how information behaved in quantum systems. This research uncovered new aspects of quantum mechanics that had been overlooked in previous interpretational debates. Quantum systems could store and process information in ways that had no classical analog, using phenomena like entanglement and superposition as computational resources. One of the most striking discoveries was quantum teleportation, the ability to transmit the complete quantum state of a particle from one location to another using only classical communication and pre-shared entanglement. The original particle was destroyed in the process, while an exact replica appeared at the destination. It was as if the particle had been disassembled at one location and perfectly reconstructed at another. Quantum teleportation didn't allow for faster-than-light communication, but it demonstrated that quantum information had properties that were fundamentally different from classical information. The experiment required that the original particle be measured and destroyed to extract the classical information needed for reconstruction. The no-cloning theorem ensured that only one copy of the quantum state could exist at any time. These developments added new dimensions to the interpretation debate. If quantum states could be teleported, what did this mean about the nature of identity and continuity? Was the teleported particle the same particle or a perfect copy? The question had no clear answer within classical physics, but quantum mechanics seemed to suggest that the distinction was meaningless. As quantum technology advanced, physicists also developed increasingly sophisticated tests of quantum mechanics itself. The theory had been confirmed in countless experiments, but there were still loopholes in the tests of fundamental phenomena like Bell's theorem. The most important loophole was the detection loophole, the fact that not all particles in entanglement experiments could be successfully detected. If the detected particles were not representative of the full ensemble, it might be possible for a local hidden variable theory to mimic the predictions of quantum mechanics. Closing this loophole required developing detectors that could capture nearly 100% of the particles in an experiment, a significant technological challenge. By the 2010s, several groups had achieved the necessary detection efficiency and performed loophole-free tests of Bell's theorem. The results continued to support quantum mechanics. Even when all known loopholes were closed, entangled particles exhibited correlations that violated Bell's inequalities. The experiments provided the strongest evidence yet that the world was fundamentally non-local or non-real in the way that classical physics had assumed. But even as experiments confirmed the predictions of quantum mechanics, new interpretations emerged to challenge the orthodox Copenhagen view. The de Broglie-Bohm theory, also known as pilot wave theory, proposed that particles had definite positions and momenta at all times, but they were guided by a quantum field that produced the observed statistical behavior. In the pilot wave interpretation, particles followed deterministic trajectories, but these trajectories were determined by a quantum potential that depended on the wave function. The wave function didn't collapse during measurement. Instead, the particle's trajectory through the wave field determined what outcome was observed. This interpretation restored realism to quantum mechanics. Particles had definite properties at all times, but at the cost of locality. The quantum potential could exert instantaneous influences across arbitrarily large distances, creating the non-local correlations observed in entanglement experiments. Pilot wave theory made the same predictions as standard quantum mechanics for all experiments, but it offered a radically different picture of what was happening at the microscopic level. Instead of particles existing in superposition, they followed definite but unknowable trajectories through space. The theory gained renewed interest in the late 20th century as physicists developed numerical techniques for calculating the particle trajectories that the theory predicted. These calculations revealed strange and beautiful patterns, quantum trajectories that crisscrossed and interfered in ways that had no classical analog. But pilot wave theory faced conceptual challenges. The quantum potential that guided particles seemed to carry information without carrying energy, violating principles that physicists had thought were fundamental. The theory also struggled to accommodate relativistic effects and field-theoretical phenomena that were crucial for understanding particle physics. Another interpretation that gained attention was the many-minds interpretation, developed by David Albert and Barry Lower. This theory suggested that wave function collapse occurred not in the physical world, but in the minds of observers. Each conscious being had multiple minds that experienced different outcomes of quantum measurements, but only one mind in each measurement chain was associated with any particular physical body. The many minds interpretation avoided some of the problems of the many worlds theory by localizing the branching process to conscious experience rather than physical reality, but it required accepting that consciousness had a fundamentally quantum nature, that each person's mind was constantly splitting into multiple streams of experience. As the 21st century began, the interpretation of quantum mechanics remained an open question, despite nearly a century of debate. Experiments had confirmed the theory's predictions with extraordinary precision, but physicists were no closer to agreeing on what those predictions meant about the nature of reality. The situation was complicated by the development of quantum field theory, which extended quantum mechanics to describe the creation and destruction of particles. In this framework, even the concept of particles became problematic. What appeared to be particles in one reference frame might appear as different numbers of particles in another frame. Quantum field theory described reality as a collection of fields that filled all of space. Particles were excitations in these fields, temporary disturbances that could appear and disappear as the fields fluctuated. Even empty space was filled with virtual particles constantly popping into and out of existence. This picture made the interpretation of quantum mechanics even more challenging. If reality consisted of quantum fields rather than particles, what did superposition mean? How could fields exist in indefinite states, and what caused them to become definite? The problem became acute when considering the quantum vacuum, the lowest energy state of quantum fields. Even in this seemingly empty state, the fields continued to fluctuate, creating virtual particles that borrowed energy from the vacuum and then annihilated before they could be directly observed. These vacuum fluctuations had measurable effects. They caused a tiny shift in the energy levels of hydrogen atoms, known as the Lamb shift, and they produced a force between closely spaced conducting plates, called the Casimir effect. The quantum vacuum wasn't empty at all. It was a seething sea of virtual particles and antiparticles. But what did it mean for particles to be virtual? They seemed to have real physical effects, but they couldn't be directly observed. Were they somehow less real than ordinary particles, or did they represent another aspect of quantum reality that defied classical categorization? The questions multiplied when physicists began to consider the application of quantum mechanics to gravity and cosmology. If quantum mechanics applied to all physical systems, it should apply to the universe as a whole. This led to the development of quantum cosmology. the attempt to understand the origin and evolution of the universe using quantum principles. In this framework, the universe itself would be described by a wave function that evolved according to the Schrödinger equation. But this raised profound questions about the nature of cosmic evolution. If the universe existed in superposition until observed, who or what could serve as an observer for the entire cosmos? Some physicists propose that the universe created its own reality through a process of self-observation. As the universe evolved and developed complex structures, these structures could serve as observers that collapsed the cosmic wave function. Consciousness might emerge as the universe's way of creating its own reality. This idea connected quantum mechanics to questions about the origin of complexity and consciousness in the universe. Perhaps the emergence of life and consciousness wasn't just a random accident, but a necessary consequence of quantum mechanics, the universe's way of becoming real through self-observation. But these speculations pushed quantum mechanics far beyond the domain where it had been experimentally tested. While the theory worked perfectly for microscopic systems, applying it to macroscopic objects and the universe as a whole required extrapolations that many physicists found questionable. The problem of the classical quantum boundary remained unsolved. Everyday objects seemed to behave classically, never exhibiting superposition or entanglement. But if quantum mechanics was fundamental, there should be no sharp boundary between quantum and classical behavior. The classical world should emerge from quantum mechanics through some process of decoherence or environmental interaction. Decoherence theory, developed in the 1980s and 1990s, proposed that quantum superpositions were destroyed by interaction with the environment. A quantum system in superposition would become entangled with its surroundings, spreading the superposition across so many degrees of freedom that it became effectively unobservable. This process could explain why large objects appeared classical. They were constantly interacting with photons, air molecules, and other environmental factors that destroyed quantum coherence almost instantaneously. The wave function didn't collapse in any fundamental sense. It just became so spread out and entangled with the environment that superposition was no longer detectable. Decoherence theory provided a promising framework for understanding the quantum to classical transition, but it didn't solve the measurement problem completely. While decoherence could explain why we didn't observe macroscopic superpositions, it didn't explain why we observed particular outcomes rather than others. The theory could account for the appearance of classical behavior, but not for the definite results of individual measurements. Recent experiments have pushed the boundaries of quantum mechanics into new regimes, creating superpositions and entanglement in increasingly large and complex systems. Researchers have demonstrated quantum effects in systems containing billions of atoms, in diamond crystals visible to the naked eye, and even in mechanical resonators that can be seen without magnification. These experiments suggest that there's no fundamental size limit to quantum effects. The boundary between quantum and classical behavior isn't determined by the number of particles in a system, but by the degree of environmental interaction and decoherence. In principle, even macroscopic objects could exhibit quantum behavior if they could be sufficiently isolated from their environment. The implications are startling. If quantum mechanics applies to all systems regardless of size, then the strange features of the quantum world, superposition, entanglement, observer effects, might be more fundamental than anyone had imagined. The classical world might be just a facade created by decoherence, hiding an underlying quantum reality where everything exists in superposition until observed. This perspective has led some physicists to embrace interpretations that seemed too radical to consider seriously in earlier decades. The many worlds interpretation, once dismissed as science fiction, has gained respectability as physicists have recognized that it provides the most straightforward reading of quantum mechanics without additional assumptions about collapse or hidden variables. In the many worlds view, the quantum wave function describes the entire reality, and there's no need to explain why it collapses because it never does. Every possible outcome of every quantum measurement occurs in some branch of the multiverse. The universe is constantly branching into parallel realities that differ in the outcomes of quantum events. This interpretation suggests that reality is far stranger than science fiction has ever imagined. Not only are there parallel universes where history unfolded differently, but new universes are being created at every moment as quantum measurements occur throughout the cosmos. The number of parallel realities is growing exponentially, with each branch subdividing further as time progresses. From this perspective, your current experience is just one thread in an infinite tapestry of possibilities. Every decision you've ever made, every quantum event in your body, every measurement performed in every laboratory on Earth has created new branches where different outcomes occurred. Parallel versions of you are reading parallel versions of these words in universes where the quantum measurements that determined your brain states produced different results. But if every possible outcome occurs in some branch of the multiverse, what determines which branch you experience? The many worlds interpretation suggests that all branches are equally real, but you can only be conscious of one branch at a time. Your consciousness somehow selects a particular path through the branching structure of reality. This raises profound questions about the nature of consciousness and personal identity. Are you the same person from moment to moment, or are you constantly being replaced by slightly different versions of yourself as the universe branches? If every possible future exists in some parallel reality, what gives meaning to the choices you make in this particular branch? Some physicists have proposed that consciousness itself might be quantum mechanical in nature. If the brain operates as a quantum computer, using superposition and entanglement to process information, then consciousness might be the mechanism that navigates the branching structure of the multiverse. This idea has led to speculative theories about quantum consciousness, suggesting that the mind's ability to collapse wave functions isn't just a metaphor, but a literal description of how consciousness works. The brain might be a quantum system that amplifies microscopic quantum events into macroscopic neural activity, allowing quantum indeterminacy to influence thought and behavior. But quantum theories of consciousness remain highly controversial. The brain appears to be a warm, wet, noisy environment where quantum coherence would be destroyed almost instantaneously by thermal fluctuations and environmental interactions. Most neuroscientists believe that neural computation is fundamentally classical, based on the flow of ions and the release of chemical neurotransmitters. Recent research has discovered quantum effects in biological systems that were previously thought to be purely classical. Photosynthesis appears to use quantum coherence to transfer energy efficiently through plant cells. Some bacteria seem to use quantum effects in their magnetic navigation systems. Even some aspects of smell and vision might involve quantum processes. These discoveries suggest that biology might have evolved to exploit quantum mechanics for functional advantages. If living systems can maintain quantum coherence despite thermal noise and environmental disturbance, perhaps the brain could also use quantum processes for computation and consciousness. But even if consciousness is quantum mechanical, this doesn't necessarily resolve the interpretation problem. A quantum brain might still face the same measurement problem as any other quantum system. How would quantum superpositions in neurons collapse to produce definite thoughts and perceptions? The question becomes even more complex when considering the possibility that consciousness might not be localized to individual brains. Some interpretations of quantum mechanics suggest that consciousness might be a fundamental property of the universe, emerging whenever information is integrated across multiple quantum systems. This panpsychist view proposes that all physical systems have some degree of consciousness or experience associated with them. Electrons might have primitive forms of experience, while complex systems like brains develop sophisticated consciousness through the integration of simpler conscious elements. In this framework, the measurement problem disappears because consciousness is present at every level of physical reality. Wave function collapse occurs whenever conscious systems observe quantum superpositions, but consciousness itself is built into the fundamental structure of the universe rather than emerging from complex arrangements of matter. But panpsychist interpretations face their own challenges. If consciousness is fundamental, why does it seem to be associated only with complex systems like brains? How do simple conscious elements combine to form unified conscious experiences? The combination problem remains unsolved in most panpsychist theories. As quantum mechanics enters its second century, the interpretation debate shows no signs of resolution. If anything, the questions have become deeper and more fundamental as physicists have explored the implications of quantum mechanics for information, computation, cosmology, and consciousness. The theory that began as an attempt to explain the spectrum of heated objects has evolved into a framework that challenges our most basic assumptions about reality, causation, and existence itself. Quantum mechanics doesn't just describe the behavior of microscopic particles, it suggests that the entire universe might operate according to principles that violate common sense and classical logic. The experimental evidence for quantum mechanics continues to accumulate, with each new test confirming the theory's predictions and ruling out classical alternatives. But the experiments only tell us what happens, not why it happens, or what it means. The question of interpretation remains as open as ever, with no clear path toward resolution. Perhaps the most unsettling possibility is that quantum mechanics is telling us something profound about the nature of reality itself, that the universe is fundamentally different from anything we could have imagined based on everyday experience. The wave-particle duality, the uncertainty principle, quantum entanglement, and the measurement problem might not be puzzles to be solved, but features of reality that we must learn to accept. If this is the case, then quantum mechanics isn't just a theory about physics, it's a revelation about the nature of existence. It suggests that reality is far more strange, subtle, and interconnected than classical science ever imagined. The universe might be a vast quantum computer processing information through superposition and entanglement, creating reality through the act of observation and measurement. In this quantum universe, consciousness might play a fundamental role not just as an observer of reality, but as a participant in its creation. The mind-matter distinction that has dominated Western thought for centuries might be an illusion created by our classical prejudices. At the deepest level, mind and matter might be different aspects of the same quantum reality, but these possibilities remain speculative, limited by our current understanding of both quantum mechanics and consciousness. The theory that has given us lasers, computers, and magnetic resonance imaging continues to resist our attempts to understand what it really means. As you settle into sleep tonight, consider the possibility that your consciousness is navigating a branching multiverse of quantum possibilities, that your dreams might be glimpses of parallel realities where different quantum measurements produced different outcomes, and that the reality you wake up to tomorrow will be just one of countless possibilities that existed until the moment you observed them. The quantum theory that breaks reality as we know it doesn't just challenge physics, it challenges every assumption about existence, consciousness, and meaning. In the quantum world, reality is not given but created, not observed but participated in, not deterministic but probabilistic. Perhaps the most profound implication of quantum mechanics is that the universe is not a machine but a creative process, constantly generating new possibilities through the interplay of measurement and consciousness. We are not passive observers of a predetermined reality, but active participants in its ongoing creation. The questions raised by quantum mechanics may never be fully answered, but they have transformed our understanding of what it means to exist in a universe where the impossible becomes possible, and where consciousness and reality are more intimately connected than we ever dared to imagine. In the quiet hours of the night, when the classical world fades into dreams and possibilities, perhaps we can glimpse something of the true nature of quantum reality, a universe of infinite potential where every moment brings new possibilities into being, and where consciousness itself might be the force that transforms possibility into actuality. The theory that began with Planck's reluctant quantum has led us to the edge of mystery itself, where science meets consciousness and where the nature of reality remains as enigmatic as ever. In this quantum universe, the journey of discovery has no end, only deeper levels of wonder and increasingly profound questions about the nature of existence itself. Time moves strangely in the quantum realm, where cause and effect can be reversed, where particles can be in two places at once, and where the future might influence the past. As consciousness fades into sleep, perhaps we enter a realm where quantum possibilities become dreams, where the branching multiverse of parallel realities becomes the landscape of the unconscious mind. Rest now in the knowledge that you exist in a universe far stranger and more wonderful than classical physics ever imagined, a quantum reality where consciousness and cosmos are partners in the ongoing dance of existence, where every moment brings new possibilities into being, and where the mystery of existence deepens with every answered question. The quantum revolution is far from over. As technology advances and our understanding deepens, we may discover that reality is even stranger than quantum mechanics suggests, or we may finally solve the puzzles that have challenged physicists for over a century. But whatever the future holds, the quantum theory has already transformed our understanding of existence in ways that will continue to influence human thought for generations to come. The mathematical precision of quantum mechanics stands in stark contrast to the philosophical chaos it has created. Consider the numbers themselves. Planck's constant, that fundamental unit of action that defines the quantum scale, has a value of approximately 6.626 times 10 to the negative 34th joule seconds. This unimaginably small number represents the minimum possible change in energy multiplied by time, the quantum of action that sets the scale at which classical physics breaks down. At room temperature, thermal energy is about 4 times 10 to the negative 21st joules, which corresponds to roughly 6 billion quanta of action. This vast number explains why we don't notice quantum effects in everyday life. Thermal fluctuations overwhelm individual quantum events by enormous margins. Yet, in carefully controlled laboratory conditions, physicists have learned to isolate and manipulate single quanta, revealing the strange world that underlies all physical reality. The precision of quantum predictions is legendary in physics. The anomalous magnetic moment of the electron, predicted by quantum electrodynamics, agrees with experimental measurements to better than 1 part in 10 to the power of 9 trillion, equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. This extraordinary accuracy makes quantum mechanics the most precisely tested theory in the history of science. Yet this mathematical precision coexists with fundamental conceptual mysteries that have resisted solution for nearly a century. The measurement problem remains as puzzling today as it was when Schrödinger devised his famous cat thought experiment. No experiment has ever directly observed a macroscopic superposition, yet the theory insists that such superpositions should exist until the moment of measurement. Recent advances in quantum technology have pushed the boundaries of what can be observed and manipulated. In 2019, researchers at the University of Vienna created quantum interference patterns using molecules containing over 2,000 atoms, objects large enough to have distinct chemical properties and three-dimensional structures. These experiments demonstrate that wave-particle duality extends far beyond the microscopic realm into a domain where quantum and classical descriptions overlap in uncomfortable ways. The molecule interference experiments reveal the subtle interplay between quantum coherence and environmental decoherence. The larger molecules remain in superposition for only brief moments before interactions with thermal photons and gas molecules destroy their quantum properties. The decoherence time decreases rapidly with molecular size, a pattern that suggests why macroscopic objects appear classical despite being made of quantum constituents. Quantum decoherence occurs through a process that is both irreversible and irreducibly statistical. When a quantum system becomes entangled with its environment, the combined system evolves unitarily according to the Schrödinger equation, but the original system appears to evolve non-unitarily as information spreads into environmental degrees of freedom that cannot be observed or controlled. The mathematics of decoherence involves partial traces over environmental states, leading to reduced density matrices that describe mixtures of quantum states rather than pure superpositions. This formalism captures the transition from quantum to classical behavior, but it doesn't solve the fundamental measurement problem. It merely pushes the problem back to the question of why we observe particular outcomes rather than others. Environmental decoherence occurs on timescales that depend dramatically on the size and complexity of the quantum system. For microscopic systems in carefully controlled laboratory conditions, coherence can persist for seconds or even minutes. For macroscopic objects at room temperature, decoherence occurs within 10 to the minus 23 seconds, a timescale so brief that it's difficult even to define what superposition would mean for such systems. But decoherence times can be extended through careful engineering. Superconducting qubits, cooled to temperatures near absolute zero and isolated from electromagnetic noise, can maintain quantum coherence for milliseconds, long enough to perform complex quantum computations. These systems exist in a liminal realm between the quantum and classical worlds, large enough to be engineered and controlled, but small enough to retain quantum properties. The field of quantum error correction has developed sophisticated techniques for preserving quantum information against the inevitable effects of decoherence. By encoding quantum information redundantly across multiple physical qubits and continuously monitoring for errors without directly measuring the encoded information, quantum error correction can, in principle, maintain quantum coherence indefinitely. The threshold theorem of quantum computing states that if the error rate per quantum operation can be reduced below approximately 10 to the power of -4, then arbitrarily long quantum computations become possible. This threshold has been achieved in several experimental systems, bringing large-scale quantum computing closer to reality. But quantum error correction comes with enormous overhead costs. The most conservative estimates suggest that a single logical qubit capable of fault-tolerant operation requires approximately 1,000 physical qubits for error correction. More realistic estimates for near-term technologies suggest overhead factors of 10,000 or more. Building a quantum computer capable of factoring large numbers, one of the most famous proposed applications, would require millions of physical qubits operating with exquisite precision. Despite these challenges, progress in quantum technology continues at an accelerating pace. Google's Sycamore processor claimed to achieve quantum supremacy in 2019 by performing a specific calculation faster than classical computers could accomplish. While the practical significance of this particular calculation remains debatable, it demonstrated that quantum computers could exploit their unique properties to achieve computational advantages over classical systems. The quantum supremacy experiment involved creating random quantum circuits that produce probability distributions that are difficult to simulate classically. The quantum processor could sample from these distributions in minutes, while classical simulation would require thousands of years on the most powerful supercomputers. This represents an exponential speedup for a specific type of problem, though not yet for problems with practical applications. IBM, Rigetti, IonQ, and other companies are developing quantum processors with different approaches to qubit implementation. Superconducting circuits, trapped ions, neutral atoms, photonic systems, and topological qubits all offer different trade-offs between coherence time, gate fidelity, connectivity, and scalability. The diversity of approaches suggests that quantum computing may follow multiple technological pathways rather than converging on a single dominant architecture. But the most profound implications of quantum mechanics may lie not in its technological applications, but in its suggestions about the fundamental nature of reality. The delayed choice quantum eraser experiments, first proposed by John Wheeler and later realized in laboratory settings, demonstrate that the wave-particle nature of light can be determined after the light has already passed through an experimental apparatus. In these experiments, photons pass through a double-slit setup, but information about which slit each photon traversed is recorded in entangled marker photons. The decision of whether to erase this witch path information can be made after the original photons have already been detected. If the information is erased, the original photons show interference patterns characteristic of wave behavior. If the information is preserved, they show particle-like behavior with no interference. The timing of these experiments rules out any classical explanation based on signals traveling at the speed of light. The decision to erase or preserve which path information appears to retroactively determine the wave or particle nature of photons that have already been detected. This suggests that the past is not fixed until it has been observed, that quantum mechanics allows for a form of retrocausality where future measurements influence past events. Wheeler interpreted these results as evidence that the universe's past is not determined until it is observed. In his participatory universe hypothesis, he suggested that observation and measurement play a fundamental role in creating the history of the cosmos. The universe's past exists in superposition until observers collapse the cosmic wave function through the act of measurement. This interpretation connects quantum mechanics to cosmology in ways that challenge our understanding of time, causality, and existence. If Wheeler is correct, then the Big Bang itself might exist in superposition, with different possible histories for the universe existing simultaneously until observers measure the cosmic microwave background and other relics of the early universe. The anthropic principle, the observation that the universe's fundamental constants seem fine-tuned for the existence of life, takes on new meaning in this context. Perhaps the universe's parameters aren't fixed by some unknown mechanism, but exist in superposition until the emergence of conscious observers who collapse the cosmic wave function into configurations compatible with their own existence. But Wheeler's participatory universe faces serious conceptual challenges. If the universe's past is determined by present observations, how did conscious observers emerge in the first place? The theory seems to require that consciousness exist before the universe has a definite history, creating a causal loop that's difficult to resolve. Some physicists have proposed that quantum mechanics might allow for truly closed time-like curves, paths through space-time that loop back to their own past. If quantum mechanics permits retrocausality, perhaps it also allows for more dramatic violations of our intuitive understanding of time and causation. Novikov's self-consistency principle suggests that any events occurring in a closed time-like curve must be self-consistent. The past cannot be changed in a way that would prevent the formation of the closed time-like curve in the first place. This principle might resolve some of the paradoxes associated with time travel, but it raises new questions about the nature of free will and determinism. Quantum mechanics might provide a framework for understanding how self-consistency could be maintained in the presence of closed time-like curves. If quantum systems exist in superposition until measured, then the measurement process might select from among the self-consistent possibilities, ensuring that paradoxes never actually arise. But these speculations push quantum mechanics far beyond the domain where it has been experimentally tested. While quantum mechanics has been confirmed in countless experiments involving microscopic systems, extending it to cosmological scales and closed time-like curves requires enormous extrapolations that may not be justified. The integration of quantum mechanics with general relativity remains one of the greatest challenges in theoretical physics. Einstein's theory describes space-time as a smooth, continuous manifold, while quantum mechanics suggests that all physical quantities should be quantized at sufficiently small scales. Reconciling these perspectives requires understanding the quantum nature of space-time itself. String theory represents one attempt to unify quantum mechanics and general relativity by proposing that fundamental particles are not point-like objects, but extended strings vibrating in higher dimensional spaces. The different vibrational modes of these strings correspond to different particles, while the geometry of the extra dimensions determines the forces and interactions between them. String theory naturally incorporates both quantum mechanics and general relativity, suggesting that they are different aspects of a more fundamental theoretical framework. But string theory makes predictions only at energy scales far beyond what can be tested with current technology, leaving its physical relevance uncertain. Loop quantum gravity takes a different approach to quantization, proposing that spacetime itself has a discrete, granular structure at the smallest scales. In this framework, area and volume are quantized, with minimum possible values determined by Planck's constant and other fundamental constants. The discretization of spacetime in loop quantum gravity leads to predictions about the quantum geometry of space and time that might be observable in cosmological settings. The theory suggests that the Big Bang might be replaced by a big bounce, a quantum transition from a contracting to an expanding universe that avoids the singularities predicted by classical general relativity. But both string theory and loop quantum gravity face significant challenges in making contact with experimental observation. The energy scales at which quantum gravitational effects become important are typically associated with black holes, neutron stars, and the early universe, environments that are difficult or impossible to study in controlled laboratory settings. The recent detection of gravitational waves by LIGO and other interferometers has opened new windows for testing general relativity in extreme environments. These observations might eventually provide indirect evidence for quantum gravitational effects, though such evidence would likely be subtle and difficult to interpret. Black holes present particularly intriguing laboratories for testing quantum mechanics in gravitational settings. Hawking's discovery that black holes emit thermal radiation with a temperature inversely proportional to their mass suggests that black holes have entropy proportional to their surface area rather than their volume. The Bekenstein-Hawking entropy formula implies that the information content of any region of space is limited by the area of its boundary rather than its volume. This holographic principle suggests that the three-dimensional world we experience might be encoded in information stored on two-dimensional surfaces, a possibility that has profound implications for our understanding of space, time, and information. Holographic duality, developed in the context of string theory, provides concrete mathematical examples of this principle. The ADS-CFT correspondence establishes an exact equivalence between certain gravitational theories in higher dimensional curved spacetime and quantum field theories on lower dimensional flat boundaries. This duality suggests that gravitational phenomena, including black holes and cosmological expansion, might be dual descriptions of quantum mechanical processes in lower dimensional systems. The correspondence has provided new tools for understanding both quantum field theory and quantum gravity, though its relevance to the actual universe remains uncertain. The black hole information paradox highlights the tension between quantum mechanics and general relativity. If black holes destroy information when they evaporate through Hawking radiation, this would violate the fundamental principle of quantum mechanics that information is always conserved. But if information escapes from black holes, it's unclear how this is possible, given that nothing can travel faster than light and escape from inside the event horizon. Recent work by Leonard Susskind, Juan Maldacena, and others has suggested that the information paradox might be resolved through quantum entanglement. If the interior of a black hole is quantum mechanically equivalent to its exterior Hawking radiation, then information might be preserved in highly entangled but observable forms. The ER equals EPR conjecture proposes that Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen entanglement. This suggests that quantum entanglement might literally create geometric connections between distant regions of space-time, providing a mechanism for information transfer that doesn't violate locality in any obvious way. But these ideas remain highly speculative and far from experimental confirmation. The quantum mechanics of black holes involves physics at energy scales and in gravitational environments that are currently inaccessible to direct observation or experimental manipulation. Perhaps the most striking feature of quantum mechanics is its non-local character, demonstrated most clearly in tests of Bell's theorem. The violation of Bell inequalities shows that either locality or realism must be abandoned. Either information can travel faster than light, or particles don't have definite properties independent of measurement. Most physicists have chosen to abandon realism rather than locality, accepting that particles don't have definite properties until they are measured. But this choice comes with its own conceptual costs, requiring that we abandon our intuitive understanding of an objective reality that exists independent of observation. The Kochen-Specker theorem provides additional evidence against realism by showing that it's impossible to assign definite values to all observables of a quantum system in a way that's consistent with the predictions of quantum mechanics. Even if we abandon locality, we cannot maintain a naive realist picture of particles having all properties simultaneously, but the violation of realism raises profound questions about the nature of physical properties and their relationship to measurement. If particles don't have definite positions and momenta until measured, what determines the outcomes of measurements? How can probabilistic laws emerge from underlying reality that has no definite properties? Some interpretations of quantum mechanics, such as cubism, quantum Bayesianism, suggest that quantum mechanics is not about reality itself, but about the beliefs and expectations of observers. In this view, quantum states represent subjective degrees of belief rather than objective features of physical systems. Cubism eliminates the measurement problem by denying that wave function collapse represents a physical process. Instead, collapse represents the updating of an observer's beliefs when new information is acquired through measurement. The quantum formalism becomes a tool for managing subjective expectations rather than a description of objective reality. But cubism faces its own conceptual challenges. If quantum mechanics is purely subjective, how do different observers achieve agreement about experimental results? Why do quantum predictions work so well if they don't describe anything objective about physical systems? The debate over the interpretation of quantum mechanics continues to generate new proposals and refinements of existing approaches. Relational quantum mechanics, developed by Carlo Rovelli, suggests that properties exist only relative to observers rather than absolutely. Different observers might disagree about the properties of quantum systems, but their disagreements are not observable because observers cannot communicate without becoming entangled with the systems they observe. Consistent histories approaches, pioneered by Murray Gell-Mann and James Hartlell, attempt to avoid the measurement problem by focusing on consistent sets of histories rather than individual measurement events. In this framework, quantum mechanics provides probabilities for different coarse-grained histories of the universe, but fine-grained questions about definite properties at specific times may not have meaningful answers. The spontaneous collapse theories, such as GRW, Ghirardi-Rimini-Weber theory, propose that wave function collapse is a genuine physical process that occurs spontaneously with a probability that increases with the number of particles in a quantum system. This approach preserves realism by suggesting that quantum systems have definite properties, but it modifies the Schrödinger equation to include stochastic collapse terms. GRW theory makes predictions that differ from standard quantum mechanics for sufficiently large systems. The theory suggests that macroscopic superpositions should collapse within measurable timescales, potentially providing experimental tests that could distinguish between collapse and no-collapse interpretations of quantum mechanics. But spontaneous collapse theories face challenges in maintaining Lorentz invariance and consistency with special relativity. The instantaneous nature of collapse processes seems to require preferred reference frames that violate the principles of relativity. As quantum mechanics approaches its second century, the interpretation debate shows no signs of resolution. Each approach to understanding the theory faces conceptual challenges and requires accepting conclusions that violate common sense in different ways. The many worlds interpretation eliminates measurement problems by accepting an exponentially branching multiverse. The Copenhagen interpretation maintains observer-induced collapse, but struggles to define what constitutes measurement. Hidden variable theories restore realism, but require non-local interactions. Consciousness-based interpretations give mind a fundamental role in physics, but conflict with materialism and evolution. Perhaps the most honest conclusion is that quantum mechanics has revealed something genuinely surprising about the nature of reality, that the universe operates according to principles that cannot be understood using the categories and concepts that evolution has provided for navigating everyday experience. The success of quantum mechanics in predicting experimental results and enabling technological applications demonstrates that the theory captures something important about physical reality, but the interpretation debates show that understanding what the theory means remains as challenging as ever. In laboratories around the world, quantum experiments continue to probe the boundaries of what can be observed and controlled. Quantum computers promise to revolutionize computation, cryptography, and simulation. Quantum sensors achieve unprecedented precision in measuring time, magnetic fields, and gravitational waves. Quantum communication protocols enable perfectly secure transmission of information, but these practical applications don't resolve the fundamental questions about what quantum mechanics means. If anything, they make the questions more urgent by demonstrating that quantum phenomena have real consequences for the macroscopic world. The quantum internet, currently under development, will connect quantum computers and sensors across global distances using quantum entanglement for communication. This technology will enable new forms of computation and sensing that exploit non-local quantum correlations, making Bell's theorem violations part of everyday technological infrastructure. Quantum radar and quantum lidar promise to detect objects with sensitivity and precision that exceeds classical limits. These applications exploit quantum entanglement between transmitted and stored photons to reduce noise and enhance signal-to-noise ratios beyond what classical systems can achieve. But perhaps the most profound applications of quantum mechanics lie in its implications for understanding consciousness, free will, and the nature of existence itself. If consciousness plays a fundamental role in wave function collapse, then the mind-matter problem that has puzzled philosophers for centuries might find its resolution in quantum mechanics. Recent research on quantum biology has discovered quantum effects in photosynthesis, avian navigation, and possibly even neural microtubules in the brain. These discoveries suggest that evolution has found ways to exploit quantum mechanics for biological functions, raising the possibility that consciousness itself might be a quantum phenomenon. The orchestrated objective reduction theory, proposed by Roger Penrose and Stuart Hameroff, suggests that consciousness emerges from quantum computational processes in microtubules within neurons. In this theory, quantum superpositions in the brain undergo objective reduction when they reach critical thresholds, creating moments of conscious experience. But quantum theories of consciousness remain highly controversial and face significant challenges from our understanding of neural decoherence and the warm, noisy environment of the brain. Most neuroscientists believe that consciousness emerges from classical computational processes rather than quantum mechanical phenomena. The hard problem of consciousness, explaining how and why physical processes give rise to subjective experience, remains unsolved regardless of whether consciousness is classical or quantum. Even if quantum mechanics plays a role in neural computation, this doesn't explain why there is something it is like to be conscious rather than nothing at all. But quantum mechanics does provide new perspectives on old philosophical problems. The measurement problem might be understood as a version of the hard problem of consciousness. How does the definite world of experience emerge from the indefinite quantum realm of possibilities? If consciousness and quantum mechanics are connected, then understanding one might require understanding the other. The interpretation of quantum mechanics and the nature of consciousness might be two aspects of the same deep mystery about the relationship between mind and physical reality. As we drift towards sleep, the quantum world continues its strange operations in the atoms and molecules of our bodies. Quantum tunneling enables the chemical reactions that sustain life. Quantum entanglement connects particles in our brains to particles throughout the universe. quantum superposition might underlie the information processing that creates our thoughts and experiences. The boundary between dreaming and waking might be understood as a transition between different regimes of quantum information processing in the brain. Dreams might represent the brain's exploration of quantum superpositions that are collapsed into definite experiences only upon waking and memory formation. In the deepest phases of sleep, when consciousness fades and the classical world dissolves, perhaps we enter a realm where quantum possibilities become directly accessible to experience. The strange logic of dreams, where cause and effect are scrambled and impossible things happen routinely, might reflect the underlying quantum structure of reality that is normally hidden by the decoherent processes of waking consciousness. But these speculations remain far beyond what current science can confirm or deny. The relationship between consciousness and quantum mechanics, if it exists at all, remains one of the deepest mysteries in science. What we can say with confidence is that quantum mechanics has revealed a universe far stranger than anyone imagined when Planck first introduced his reluctant quantum. The theory that began as a technical solution to a specific problem in black body radiation has evolved into a framework that challenges our most fundamental assumptions about reality, consciousness, and existence. The implications continue to unfold as technology advances and our understanding deepens. Each new quantum experiment reveals aspects of reality that seem impossible from a classical perspective. Each new interpretation of the theory suggests different possibilities for understanding the nature of existence. Perhaps the most remarkable aspect of the quantum revolution is that it occurred at all, that human minds evolved to navigate a classical world of medium-sized objects moving at moderate speeds, could discover and mathematically describe phenomena that violate every intuition about how reality should operate, represents one of the greatest achievements in the history of thought. The quantum theory that breaks reality as we know it doesn't just challenge physics, it challenges every comfortable assumption about the nature of existence. In discovering the quantum world, we have discovered that reality is far more mysterious, creative, and interconnected than we ever dared to imagine. Rest now in this quantum universe where possibilities collapse into actuality through the mysterious process of observation, where consciousness and cosmos might be intimately connected, and where the very act of dreaming might be a journey into the realm of quantum possibilities that underlies all existence. The mystery deepens with every answered question, and the journey into the quantum realm has only just begun. The quantum measurement problem extends far beyond academic philosophy when we consider the practical implications for emerging technologies. Quantum sensors, which exploit superposition and entanglement to achieve measurement precision beyond classical limits, operate in a regime where the boundary between quantum and classical becomes operationally important rather than merely conceptually puzzling. The atomic clocks that form the backbone of global positioning systems already rely on quantum mechanical transitions in cesium atoms, achieving precision of 1 part in 10 to the 15th. But next-generation optical atomic clocks, using transitions in ions like aluminum or strontium, promise precision approaching 1 part in 10 to the 19th power, equivalent to losing less than 1 second over the entire age of the universe. Such extraordinary precision makes these clocks sensitive to gravitational time dilation effects from elevation changes as small as centimeters. Einstein's general relativity, combined with quantum mechanics, creates measurement devices so precise that they can detect the gravitational field variations caused by underground water movement, tectonic activity, and even the passage of gravitational waves from distant cosmic events. The advanced LIGO gravitational wave detectors represent perhaps the most ambitious attempt to combine quantum mechanics with general relativity in a practical measurement device. These instruments use laser interferometry to detect changes in arm length smaller than 10 to the minus 19 meters, roughly 1/10,000th the width of a proton. At this scale, quantum noise from vacuum fluctuations becomes the limiting factor in measurement precision. To overcome the quantum noise limit, advanced LIGO uses squeezed light, a quantum optical technique that redistributes uncertainty between different quadratures of the electromagnetic field. By squeezing vacuum noise below its standard quantum limit in the measurement quadrature, the detectors can achieve sensitivity levels that would be impossible with classical light sources. The successful detection of gravitational waves from merging black holes and neutron stars has opened an entirely new window for observing the universe, but it has also demonstrated that quantum mechanics operates even in experiments designed to test general relativity. The quantum nature of light places fundamental limits on how precisely we can measure space-time curvature, creating an intimate connection between quantum mechanics and gravitation that extends beyond theoretical speculation. Quantum-enhanced sensing extends to magnetic field measurements through nitrogen vacancy centers in diamond crystals. These quantum defects can detect magnetic field variations as small as femtoteslas, magnetic fields millions of times weaker than Earth's magnetic field. Such sensitivity enables quantum magnetometry of single molecules, individual cells, and neural activity in living brains. The nitrogen vacancy centers operate as quantum magnetic field sensors by using the spin states of individual electrons trapped at crystal defects. Microwave pulses can manipulate these spins into superposition states that are sensitive to magnetic field fluctuations. The measurement process involves optical pumping and fluorescence detection, creating a quantum sensor that bridges the gap between individual atomic systems and macroscopic measurement apparatus. But these quantum sensors operate in a measurement regime where the classical quantum boundary becomes experimentally relevant. The sensors must remain quantum mechanically coherent during the sensing period to achieve enhanced sensitivity, but they must also interact with their environment strongly enough to detect external signals. This trade-off between coherence and sensitivity creates practical constraints that mirror the theoretical challenges of the measurement problem. Quantum biology has emerged as a field where quantum mechanical effects appear to play functional roles in living systems, challenging the assumption that biological processes are necessarily classical. Photosynthetic energy transfer in plants and bacteria exhibits quantum coherence that persists for hundreds of femtoseconds. Despite the warm, noisy biological environment, the discovery of quantum effects in photosynthesis began with ultra-fast spectroscopy experiments that revealed oscillating signals in energy transfer dynamics. These oscillations suggested that electronic excitations in photosynthetic complexes exist in quantum superpositions that sample multiple energy transfer pathways simultaneously before settling into the most efficient route. Computer simulations of photosynthetic energy transfer demonstrate that quantum coherence can enhance efficiency by allowing excitations to explore multiple pathways in parallel and select the optimal route to the reaction center. This quantum enhancement appears most pronounced in intermediate coupling regimes, where neither purely coherent nor purely incoherent energy transfer would be optimal. The persistence of quantum coherence in biological systems at room temperature suggests that evolution has found ways to exploit quantum mechanics for functional advantages. Protein structures appear to be optimized to maintain coherence for just long enough to enable efficient energy transfer while preventing decoherence timescales from becoming so long that thermal fluctuations disrupt the process. Similar quantum effects have been discovered in other biological systems. European robins appear to use quantum entanglement in their eyes for magnetic navigation, with cryptochrome proteins creating entangled radical pairs whose spin states are sensitive to Earth's magnetic field. The quantum nature of this compass mechanism explains the bird's ability to see magnetic field lines as visual patterns overlaid on their normal vision. Even more speculatively, some researchers have proposed that quantum effects might play roles in neural computation and consciousness. The microtubules that form part of the cellular cytoskeleton in neurons have been suggested as possible sites for quantum processing, though the warm, wet environment of the brain presents significant challenges for maintaining quantum coherence. Stuart Hameroff and Roger Penrose have developed the most detailed quantum theory of consciousness, proposing that quantum computations in microtubules underlie conscious experience. In their model, quantum superpositions in tubulin proteins accumulate until they reach a threshold for objective reduction, a hypothetical physical process that collapses the superposition and creates a moment of conscious experience. The OR theory faces significant criticism from neuroscientists and physicists who question whether quantum coherence can survive in the noisy environment of neural tissue. Decoherence calculations suggest that any quantum superpositions in microtubules would collapse within femtoseconds, far too quickly to influence neural processing that occurs on timescales of milliseconds or longer. But recent experiments have demonstrated quantum coherence in biological systems under conditions that theoretical models predicted would destroy quantum effects almost instantaneously. These discoveries suggest that our understanding of decoherence in complex systems may be incomplete, particularly when those systems have been optimized by evolution to exploit quantum effects. The relationship between quantum mechanics and consciousness remains highly speculative, but it touches on some of the deepest questions in science. If consciousness involves quantum effects, then the measurement problem in quantum mechanics might be related to the hard problem of consciousness, how and why physical processes give rise to subjective experience. Some interpretations of quantum mechanics explicitly invoke consciousness as the mechanism for wave function collapse. In these theories, conscious observation is what transforms quantum possibilities into classical realities. But this creates a circular relationship where consciousness both emerges from quantum processes and determines which quantum processes occur. The global workspace theory of consciousness, developed by Bernard Bars and later refined by Stanislas Dehaene and others, proposes that consciousness involves the global broadcasting of information across different brain regions. If this broadcasting involves quantum entanglement between neural networks, it might explain how distributed brain activity becomes unified into coherent conscious experience. But even if consciousness involves quantum effects, this doesn't necessarily resolve the interpretation problem in quantum mechanics. A quantum brain would still face the measurement problem when its quantum states needed to collapse into definite neural activity patterns that correspond to specific thoughts and perceptions. The emergence of quantum artificial intelligence represents another frontier where quantum mechanics intersects with information processing and possibly consciousness. Quantum machine learning algorithms can potentially process information in ways that have no classical analog, using superposition and entanglement to explore solution spaces that would be inaccessible to classical computers. Quantum neural networks have been proposed that could exploit quantum parallelism to perform pattern recognition and optimization tasks with exponential speedups over classical approaches. These systems might naturally exhibit some of the features that make consciousness mysterious: the binding of distributed information into unified representations, the apparent non-algorithmic aspects of creative insight, and the subjective quality of experience. But whether artificial quantum systems could be conscious raises philosophical questions that go beyond the technical challenges of building quantum computers. If consciousness requires biological substrates or specific physical processes that occur only in evolved brains, then quantum AI might achieve superintelligent capabilities without ever experiencing anything subjective. The development of quantum technologies is also creating new ethical and social challenges that echo some of the philosophical puzzles of quantum mechanics. Quantum cryptography promises perfectly secure communication, but it also enables surveillance capabilities that could be used for authoritarian control. Quantum computers threaten to break the encryption protocols that protect financial transactions and personal privacy, requiring the development of entirely new approaches to information security. More speculatively, if the many worlds interpretation is correct and quantum computers can access computational resources from parallel universes, then quantum computing might involve ethical obligations to conscious beings in other branches of the multiverse. The decisions we make about quantum experiments and computations might affect countless parallel versions of ourselves and others. The cosmological implications of quantum mechanics continue to generate new theoretical frameworks and empirical predictions. Eternal inflation, driven by quantum fluctuations in scalar fields during the early universe, predicts that our observable universe is just one bubble in an infinite multiverse where every possible physical law and initial condition is realized somewhere. In this cosmological multiverse, quantum mechanics operates on the largest possible scales. The universe as a whole exists in a superposition of different expansion histories, different laws of physics, and different arrangements of matter and energy. The anthropic principle becomes a selection effect. We observe a universe compatible with our existence because conscious observers can only emerge in regions where the physical constants permit complex structures to form. Quantum cosmology attempts to apply the principles of quantum mechanics to the universe as a whole, treating space-time itself as a quantum system described by a universal wave function. The Wheeler-DeWitt equation, which combines general relativity with quantum mechanics, describes the evolution of this cosmic wave function, but it faces severe technical and conceptual challenges. The problem of time in quantum cosmology arises because general relativity treats time as part of the dynamical space-time geometry, while quantum mechanics requires a fixed temporal parameter to describe evolution. If space-time is quantized, then time itself might emerge from more fundamental quantum processes, creating a bootstrap problem where quantum evolution requires time, but time requires quantum evolution. Some approaches to quantum cosmology, such as causal set theory, propose that space-time has a discrete, granular structure at the Planck scale. In this framework, time emerges from the causal relationships between discrete space-time events, with quantum mechanical evolution arising from the probabilistic nature of these causal connections. The holographic principle, derived from black hole thermodynamics, suggests that all the information contained in any volume of space can be encoded on its boundary surface. This principle has led to the development of holographic cosmology, where the entire universe is described as information processed on a distant boundary surface. In holographic cosmology, the three-dimensional space we experience might be a holographic projection of information processing on the cosmic horizon. This perspective suggests that the universe might literally be a quantum information processing system, with space-time and matter emerging from more fundamental computational processes. The holographic principle also provides new perspectives on the black hole information paradox. If the information falling into a black hole is encoded holographically on the event horizon, then it never actually disappears from the perspective of external observers. The apparent loss of information might be an artifact of trying to describe quantum information using classical space-time concepts. Recent developments in quantum error correction have provided new tools for understanding how information might be preserved in black hole evaporation. The quantum error correcting codes that protect information in quantum computers might also protect information in black holes, with Hawking radiation serving as a noisy quantum channel that can, in principle, reconstruct the original information that formed the black hole. These connections between quantum information theory and black hole physics suggest deep relationships between computation, thermodynamics, and space-time geometry. The universe might be fundamentally computational in nature, with the laws of physics emerging from information processing constraints rather than being imposed from outside the physical system. But these theoretical developments remain far from experimental confirmation. The energy scales associated with quantum gravity and black hole physics are typically far beyond what can be achieved in terrestrial laboratories. Most tests of quantum mechanics continue to involve systems that are large compared to the Planck scale, but small compared to everyday objects. The gap between the quantum scale and the scale of classical experience represents one of the most significant challenges in extending our understanding of quantum mechanics. While we can manipulate individual atoms and photons with remarkable precision, we still cannot create macroscopic superpositions that would directly reveal the quantum nature of everyday objects. Recent proposals for macroscopic quantum experiments involve levitating microscopic diamonds or mirrors in optical traps and cooling them to quantum mechanical ground states. These systems would be large enough to observe directly while remaining sufficiently isolated from their environment to maintain quantum coherence. Gravitational wave detectors represent natural laboratories for testing quantum mechanics at macroscopic scales. The advanced LIGO mirrors, each weighing 40 kilograms, are among the most isolated macroscopic objects ever created, with thermal noise reduced to quantum mechanical limits. Future gravitational wave detectors might achieve sensitivity levels where quantum effects become observable in the motion of these massive test objects, but creating macroscopic superpositions remains an extraordinary technical challenge. The decoherence times for large objects are so brief that maintaining coherence requires isolation from all environmental influences, including thermal photons, gas molecules, and electromagnetic fields. Each additional atom in a quantum system typically reduces the coherence time by orders of magnitude. The practical limitations on macroscopic quantum experiments mean that many interpretational questions about quantum mechanics might never be settled by direct observation. We may need to accept that some aspects of quantum reality remain forever beyond empirical access, leaving the interpretation debate to be resolved through theoretical considerations and philosophical arguments rather than experimental tests. This situation is unusual in the history of science, where theoretical disputes have typically been resolved by crucial experiments that distinguish between competing hypotheses. The interpretation of quantum mechanics might represent a fundamentally different type of scientific question, one where the empirical content is exhausted by the mathematical formalism, leaving interpretational questions as matters of preference rather than fact. But the interpretational debates in quantum mechanics are not merely academic exercises. They influence how physicists think about reality, causation, and the relationship between mind and matter. Different interpretations suggest different possibilities for future theoretical developments and technological applications. The many worlds interpretation suggests that quantum computers might be accessing computational resources from parallel universes, raising questions about the nature of quantum speedups and the ultimate limits of quantum computation. If quantum algorithms are literally performed in parallel across multiple universes, then quantum computers might achieve capabilities that seem impossible from a single universe perspective. The consciousness-based interpretations suggest that artificial intelligence systems might need to incorporate quantum effects to achieve true consciousness or general intelligence. If consciousness plays a fundamental role in quantum mechanics, then understanding consciousness might be necessary for developing advanced AI systems or for predicting the behavior of quantum computers. The pilot wave interpretation suggests that quantum particles have definite trajectories that are guided by quantum fields, opening possibilities for controlling quantum systems in ways that other interpretations would consider impossible. If particles have definite positions and momenta at all times, then precision measurement and control might be limited by practical rather than fundamental constraints. But these interpretational differences might ultimately prove irrelevant for technological applications. Quantum computers work regardless of whether their quantum states exist in many worlds, collapse through consciousness, or follow hidden variable trajectories. The mathematical formalism of quantum mechanics provides accurate predictions for all experimental outcomes, independent of what that formalism might mean about the nature of reality. This instrumentalist approach to quantum mechanics has dominated the field since the early days of the Copenhagen interpretation. Most working physicists use quantum mechanics as a tool for calculation and prediction without worrying about what the theory implies about the fundamental nature of reality. But the instrumentalist approach becomes problematic when quantum mechanics is extended to cosmology and consciousness, domains where human observers are part of the system being described rather than external to it. Cosmological applications of quantum mechanics require understanding what the universal wave function means, while applications to consciousness require understanding the relationship between quantum states and subjective experience. These challenges suggest that the interpretational questions in quantum mechanics might be more than philosophical luxuries. Understanding what quantum mechanics means might be necessary for extending the theory to new domains and for developing technologies that exploit quantum effects in complex systems. The quantum internet represents one emerging technology where interpretational questions might have practical implications. Quantum networks will use entanglement distribution and quantum teleportation to connect quantum computers and sensors across global distances, creating a technological infrastructure that relies on the most mysterious aspects of quantum mechanics. Managing quantum entanglement across large networks requires understanding how entanglement behaves under decoherence, measurement, and environmental noise. Different interpretations of quantum mechanics suggest different approaches to maintaining and manipulating entangled states in realistic conditions. The security of quantum cryptographic protocols depends on fundamental features of quantum mechanics, such as the no-cloning theorem and the impossibility of measuring complementary observables simultaneously. If these features have loopholes or interpretational ambiguities, they might create vulnerabilities in quantum communication systems, but practical quantum technologies have generally confirmed the standard predictions of quantum mechanics without resolving interpretational disputes. Quantum computers, quantum sensors, and quantum communication systems all work as expected based on the mathematical formalism, regardless of competing interpretations of what that formalism means. Perhaps the most profound implication of quantum mechanics is not any particular interpretation, but the simple fact that reality operates according to principles that violate human intuition so completely. The measurement problem, wave-particle duality, quantum entanglement, and the uncertainty principle all demonstrate that the universe is fundamentally different from anything we could have imagined based on everyday experience. This suggests that human cognition, which evolved to navigate a classical world of medium-sized objects moving at moderate speeds, might be inherently limited in its ability to understand the deepest features of reality. The success of quantum mechanics might represent the triumph of mathematical abstraction over intuitive understanding. If this is correct, then future advances in physics might require abandoning intuitive pictures of reality entirely and working with purely mathematical structures that have no classical analogies. String theory, loop quantum gravity, and other approaches to quantum gravity already operate in this regime, describing reality using mathematical concepts that cannot be visualized or understood in everyday terms. But the limitations of human intuition might not represent absolute barriers to understanding. The development of quantum mechanics itself demonstrates that humans can discover and work with concepts that initially seem impossible or contradictory. Each generation of physicists becomes more comfortable with quantum concepts that seemed paradoxical to their predecessors. Future developments in virtual reality, brain-computer interfaces, and artificial intelligence might provide new tools for developing intuition about quantum mechanical phenomena. If we can create immersive simulations of quantum systems or augment human cognition with quantum computing capabilities, we might develop new forms of understanding that transcend the limitations of classical intuition. The quantum world might not remain forever mysterious. As we develop new tools for visualizing and manipulating quantum systems, and as quantum effects become part of everyday technology rather than exotic laboratory phenomena, the concepts of quantum mechanics might become as familiar and intuitive as classical mechanics is today. But regardless of whether quantum mechanics eventually becomes intuitive, it has already transformed our understanding of the nature of existence in fundamental ways. The theory that began with Planck's reluctant quantum has revealed a universe where reality is created through observation, where information can be transmitted instantaneously across arbitrary distances, and where consciousness might play a fundamental role in determining physical events. These discoveries represent some of the most profound advances in human knowledge, comparable to the Copernican revolution that displaced Earth from the center of the universe, or the Darwinian revolution that connected humans to the broader tree of life. Quantum mechanics has displaced classical reality from its privileged position and revealed a universe that is far stranger, more interconnected, and more mysterious than anyone could have imagined. The journey into quantum reality continues to unfold as new experiments push the boundaries of what can be observed and controlled. Each advance in quantum technology reveals new aspects of quantum mechanics while raising new questions about the nature of reality and consciousness. Perhaps the most remarkable aspect of this journey is that it represents a collaboration between human consciousness and the quantum universe itself. Every quantum experiment involves the interaction of conscious observers with quantum systems, creating a feedback loop where consciousness both discovers and participates in the creation of quantum reality. In the end, quantum mechanics might be telling us something profound about the relationship between mind and universe, that they are not separate entities, but different aspects of a deeper unity that includes both consciousness and quantum mechanics as complementary descriptions of a reality that transcends both. As consciousness fades into sleep and dreams, we enter a realm where the classical categories of waking experience dissolve and are replaced by the fluid, probabilistic logic of the quantum world. In dreams, multiple possibilities coexist simultaneously, impossible events occur routinely, and the past and future interpenetrate in ways that mirror the temporal paradoxes of quantum mechanics. Perhaps sleep and dreams provide the closest natural analog we have to quantum consciousness, a state where the classical ego that navigates everyday reality gives way to more fundamental processes that operate according to quantum principles of superposition, entanglement, and non-locality. The quantum theory that breaks reality as we know it ultimately suggests that reality as we know it might be just the surface layer of something far more profound and mysterious. Beneath the classical world of definite objects and determinate events lies a quantum realm of infinite possibility, where consciousness and cosmos participate together in the ongoing creation of existence itself. Rest now in this quantum universe, where every moment brings new possibilities into being, where consciousness and reality are intimately connected, and where the mystery of existence deepens with every answer we discover. The philosophical implications of quantum mechanics extend beyond physics into questions that have occupied human thought since ancient times. The relationship between appearance and reality, the nature of knowledge and observation, and the role of consciousness in determining experience all take on new dimensions when viewed through the lens of quantum theory. Plato's allegory of the cave, where prisoners mistake shadows on a wall for reality itself, finds unexpected resonance in quantum mechanics. The classical world we experience might be the shadow of a deeper quantum reality, a projection of quantum processes onto the screen of macroscopic experience. The prisoner's release from the cave parallels the scientist's journey from classical intuition to quantum understanding, but quantum mechanics suggests something even more radical than Plato imagined. In the cave allegory, there is a true reality casting shadows that creates false appearances. Quantum mechanics suggests that the distinction between appearance and reality might be meaningless, that the quantum world doesn't have definite properties independent of observation, making the shadows as real as anything else. The ancient Greek atomists, particularly Democritus, proposed that reality consisted of indivisible particles moving in void space. Quantum field theory has revealed that this picture is almost exactly backward. What we call particles are temporary excitations in fields that fill all space, while the vacuum is far from empty, but seethes with virtual particles and quantum fluctuations. Yet the atomist insight that reality has a granular structure at its foundation proves remarkably prescient. Energy, angular momentum, and electric charge all come in discrete units determined by fundamental constants. Even space-time itself might have an atomic structure at the Planck scale, with discrete units of length and time that cannot be subdivided further. The Planck length, approximately 10 to the negative 35th meters, represents the scale at which quantum effects become comparable to gravitational effects. At this scale, the uncertainty principle prevents the precise localization of objects within regions smaller than their own Schwarzschild radius, suggesting that space-time itself becomes indefinite and probabilistic. Similarly, the Planck time of approximately 10 to the power of negative 43 seconds might represent the fundamental quantum of temporal experience. If time is quantized at this scale, then the smooth flow of time we experience is an emergent property of more fundamental discrete processes, analogous to how the smooth motion of a film emerges from discrete still frames. These quantum scales are so far removed from everyday experience that they challenge our ability to think meaningfully about the foundations of reality. The Planck length is smaller than atomic nuclei by the same factor that atomic nuclei are smaller than human beings. At such scales, the classical concepts of space, time, and causation might lose their meaning entirely. String theory proposes that at these fundamental scales, the point-like particles of conventional physics are replaced by one-dimensional strings whose vibrational patterns determine their apparent properties. In this framework, electrons, photons, and all other particles are different vibrational modes of the same underlying string-like entities. The mathematics of string theory requires additional spatial dimensions beyond the three we experience, typically 6 or 7 extra dimensions that are compactified or curled up at every point in ordinary space. The geometry of these hidden dimensions determines the apparent laws of physics, including the masses of particles, the strengths of forces, and the fundamental constants of nature. But string theory faces the challenge of making contact with experimental observation. The theory naturally operates at the Planck scale, where direct experimental access is impossible, and it makes few definitive predictions for phenomena at experimentally accessible energies. The theory's vast landscape of possible vacuum states, perhaps 10 to the power of 500 different ways to compactify the extra dimensions, makes it difficult to extract unique predictions. Loop quantum gravity takes a different approach to quantum spacetime, proposing that space has a discrete network structure at the Planck scale. In this picture, spacetime consists of quantized loops and nodes that carry discrete units of area and volume, with the smooth spacetime of general relativity emerging only at larger scales. The loop quantum gravity approach leads to specific predictions about the quantum geometry of spacetime that might be observable in cosmological settings. The theory suggests that the Big Bang singularity is replaced by a quantum bounce, where a contracting universe transitions smoothly into an expanding universe one, avoiding the infinite densities predicted by classical general relativity. These quantum gravity theories attempt to resolve some of the deepest paradoxes in physics, including the black hole information paradox and the nature of cosmological singularities, but they also raise new questions about the relationship between quantum mechanics and general relativity that go to the heart of our understanding of space, time, and causation. The holographic principle, emerging from black hole thermodynamics, suggests that all the information contained within any volume of space can be encoded on its boundary surface. This principle has profound implications for understanding the nature of space, information, and reality itself. If the holographic principle is correct, then the three-dimensional world we experience is analogous to a hologram, a two-dimensional encoding of information that creates the appearance of depth and volume. Our entire universe might be information processed on a distant two-dimensional surface, with the illusion of three-dimensional space emerging from the complex patterns of information storage and processing. The ADS-CFT correspondence provides a concrete mathematical example of holographic duality, establishing an exact equivalence between certain theories of quantum gravity in curved spacetime and quantum field theories on flat boundaries. This correspondence has become one of the most important tools in theoretical physics, providing insights into both quantum gravity and strongly coupled quantum systems. but the ADS-CFT correspondence applies to anti-de Sitter spacetimes that are very different from our expanding universe. Whether similar holographic dualities exist for realistic cosmological settings remains an open question, though recent work on de Sitter holography suggests that our universe might indeed be holographically dual to quantum information processing on its cosmic horizon. The implications of holographic cosmology are staggering. If our universe is holographically encoded, then the fundamental reality might be information processing rather than matter and energy moving through space and time. The laws of physics would emerge from computational constraints rather than being imposed from outside the system. This information-theoretic view of reality connects quantum mechanics to computation in ways that might resolve some interpretational puzzles. If reality consists of quantum information processing, then the measurement problem becomes a question about how information is encoded and decoded rather than how quantum states collapse into classical properties. Recent developments in quantum error correction provide tools for understanding how information can be preserved and processed in noisy quantum systems. The codes that protect quantum information from decoherence might also protect physical information in black holes and cosmological horizons, ensuring that information is never truly lost, even in the most extreme environments. But these theoretical developments remain far ahead of experimental confirmation. Testing quantum gravity and holographic duality requires energies or cosmological observations that push the boundaries of what's technologically feasible. Most tests of fundamental physics continue to operate in regimes where quantum mechanics and general relativity can be treated separately. The Large Hadron Collider, operating at energies up to 13 TeV, probes energy scales that are enormous by everyday standards, but still far below the Planck scale, where quantum gravitational effects become important. Even cosmic ray particles with energies exceeding 10 to the 20 electron volts carry energies that are 17 orders of magnitude below the Planck scale. This vast separation between experimentally accessible energies and theoretically interesting scales means that much of fundamental physics must rely on indirect evidence and theoretical consistency rather than direct experimental confirmation. The situation is unprecedented in the history of science, where theoretical progress has typically been closely connected to experimental discoveries, but quantum mechanics itself shows that fundamental limits on observation don't necessarily prevent scientific understanding. The uncertainty principle means that we can never simultaneously observe all properties of quantum systems, yet quantum mechanics provides extraordinarily accurate predictions for everything we can observe. Perhaps theories of quantum gravity will similarly provide understanding of domains that are fundamentally inaccessible to direct observation. The development of quantum technologies continues to provide new tools for probing the boundaries between quantum and classical physics. Quantum computers, quantum sensors, and quantum communication systems all operate in regimes where quantum effects are macroscopically observable, potentially providing new windows into fundamental physics. Quantum computers operating with thousands of qubits might reveal new insights into the nature of quantum entanglement and information processing that are relevant for understanding black holes and cosmology. The scaling laws for quantum error correction might provide clues about how information is processed in gravitational systems. Quantum sensors with unprecedented precision might detect gravitational effects that probe the interface between quantum mechanics and general relativity. The next generation of gravitational wave detectors might observe quantum effects in spacetime itself, revealing how quantum mechanics modifies Einstein's equations at microscopic scales. But perhaps the most profound implications of quantum mechanics lie not in its technological applications, but in its challenges to our understanding of consciousness and free will. If quantum mechanics provides the complete description of physical reality, then human consciousness and decision-making must somehow emerge from quantum processes in the brain. The hard problem of consciousness, explaining how and why physical processes give rise to subjective experience, becomes even harder if those physical processes are quantum mechanical rather than classical. How does the indefinite quantum world of superpositions and probabilities give rise to the definite world of conscious experience? Some theories propose that consciousness involves the collapse of quantum superpositions in the brain, with each moment of conscious experience corresponding to a measurement-like process that selects definite outcomes from quantum possibilities. But this raises the question of what triggers these collapse events and why they produce unified conscious experiences rather than fragmented perceptions. Other approaches suggest that consciousness emerges from quantum information processing that doesn't require wave function collapse. In this view, conscious experiences arise from complex patterns of quantum entanglement and interference that can exist without definite classical outcomes. The relationship between consciousness and free will becomes particularly complex in the quantum context. Classical determinism suggests that free will is illusory because all future states are determined by past states and natural laws. Quantum indeterminism introduces genuine randomness, but doesn't obviously restore meaningful choice. Random events seem no more freely chosen than determined ones, but some interpretations of quantum mechanics suggest more subtle relationships between consciousness and physical causation. If consciousness plays a role in selecting which quantum outcomes become real, then conscious choice might influence physical events in ways that transcend the classical distinction between determinism and randomness. The many worlds interpretation suggests that all possible choices occur in different branches of the multiverse, with conscious experience tracking particular paths through the branching structure of reality. In this view, free will might involve the selection of which branch of reality consciousness follows, rather than the determination of which events occur. But these speculations remain far beyond what current science can confirm or deny. The relationship between quantum mechanics and consciousness involves some of the deepest unsolved problems in both physics and neuroscience, with little experimental evidence to guide theoretical development. Recent advances in neurotechnology are beginning to provide new tools for investigating the physical basis of consciousness. Brain-computer interfaces can read neural signals with increasing precision and spatial resolution, potentially revealing whether quantum effects play functional roles in neural computation. The development of quantum sensors sensitive enough to detect magnetic fields from individual neurons might reveal whether the brain uses quantum entanglement for information processing. If neural computation involves quantum effects, it might show up as non-classical correlations between neural signals that cannot be explained by classical physics. But the warm, wet, noisy environment of the brain presents significant challenges for quantum effects. Most calculations suggest that quantum coherence would be destroyed within femtoseconds by thermal fluctuations and environmental interactions, making quantum effects irrelevant for neural computation that occurs on millisecond timescales. However, recent discoveries of quantum effects in biological systems suggest that these theoretical calculations might underestimate biologies to maintain quantum coherence in complex environments. Evolution has had billions of years to optimize biological systems for functional performance, possibly including the exploitation of quantum effects where they provide advantages. The discovery of quantum effects in photosynthesis demonstrates that biological systems can maintain quantum coherence for hundreds of femtoseconds despite thermal noise. While still brief by neural processing standards, these timescales suggest that quantum effects might be more robust in biological systems than previously thought. Microtubules in neurons have been proposed as possible sites for quantum processing, with some researchers suggesting that quantum effects in tubulin proteins could influence neural computation. But experimental tests of quantum effects in microtubules remain technically challenging and have produced ambiguous results. The relationship between quantum mechanics and consciousness remains one of the deepest mysteries in science. Whether consciousness involves quantum effects, classical computation, or some combination of both, the emergence of subjective experience from objective physical processes continues to challenge our understanding of the nature of reality. But regardless of whether consciousness is quantum mechanical, the interpretational puzzles of quantum mechanics themselves suggest deep connections between mind and reality. the measurement problem, the role of observation in determining outcomes, and the apparent dependence of physical properties on measurement all suggest that consciousness and physical reality are more intimately connected than classical physics supposed. The ancient question of whether mind and matter are separate substances or different aspects of a single reality takes on new urgency in the context of quantum mechanics. If physical systems don't have definite properties independent of observation, then the classical distinction between subjective experience and objective reality becomes problematic. Perhaps the most radical possibility is that consciousness and quantum mechanics are describing the same underlying reality from different perspectives. Mind might be the intrinsic nature of what we describe externally as quantum mechanics, while quantum mechanics might be the mathematical structure of what we experience intrinsically as consciousness. This perspective suggests that the hard problem of consciousness and the measurement problem in quantum mechanics are two aspects of the same puzzle: the relationship between subjective experience and objective description. Solving one might require solving the other, but these possibilities remain highly speculative and far from scientific confirmation. The relationship between mind and quantum mechanics, if it exists, operates in domains where controlled experimentation is extremely difficult and where theoretical understanding remains fragmentary. As quantum technologies advance and our understanding of both quantum mechanics and consciousness deepens, new opportunities may emerge for investigating these connections. Quantum computers might provide models for understanding how complex information processing can emerge from simple quantum operations. Brain imaging technologies might reveal whether neural computation involves quantum effects, but perhaps the most important lesson of quantum mechanics is that reality is far stranger and more subtle than our everyday experience suggests. The theory that began with Planck's quantum has revealed a universe where the impossible becomes possible, where consciousness and cosmos might be intimately connected, and where the nature of existence remains fundamentally mysterious. The quantum world operates according to principles that violate every intuition about how reality should behave, yet these same principles enable the technologies that are transforming human civilization. This paradox, that the most counterintuitive theory in physics is also the most practically successful, suggests that our intuitions about reality are fundamentally unreliable guides to the nature of existence. Perhaps this is the deepest lesson of quantum mechanics, that understanding reality requires abandoning the comfortable assumptions of everyday experience and embracing possibilities that initially seem impossible or contradictory. The universe might be far more creative, interconnected, and mysterious than we have yet imagined. As consciousness fades into the quantum realm of dreams and possibilities, we might glimpse something of the true nature of reality, a universe where mind and matter, possibility and actuality, time and eternity interpenetrate in ways that transcend classical logic and open infinite possibilities for existence itself. In the deep quiet of the night, where classical boundaries dissolve and quantum possibilities flourish, rest in the knowledge that you exist in a universe of unlimited creativity and mystery, where every moment brings new possibilities into being, and where the deepest questions about existence remain wonderfully, eternally open. The quantum theory that breaks reality as we know it ultimately reveals that reality as we know it is just the beginning of a mystery that deepens with every discovery, inviting us into an endless exploration of the nature of existence itself. In this quantum cosmos, the journey of understanding has no final destination, only deeper levels of wonder and increasingly profound questions about what it means to exist in a universe where everything is possible and nothing is certain except the eternal mystery of being itself. The precision with which quantum mechanics describes the microscopic world becomes even more remarkable when we examine the specific numerical predictions it makes. The fine structure constant, approximately 1/137, appears throughout quantum electrodynamics and determines the strength of electromagnetic interactions. This dimensionless number has puzzled physicists since its discovery. Why does nature choose this particular value rather than any other? Richard Feynman once described the fine structure constant as one of the greatest mysteries in physics, a pure number that determines how strongly electrons couple to photons. If this constant were significantly different, atoms would be unstable, chemistry would be impossible, and life could not exist. The precise value of 137.036 seems to be fine-tuned for the existence of complex structures in the universe. Similarly, the electron's anomalous magnetic moment, measured to 12 decimal places, provides one of the most precise tests of quantum field theory. The theoretical prediction, calculated using Feynman diagrams that sum over all possible virtual particle interactions, agrees with experiment to better than 1 part in a trillion. This extraordinary precision demonstrates that quantum field theory correctly describes the behavior of electrons and photons. Even various approaches have been proposed to resolve this crisis, including supersymmetry, which predicts that every particle has a superpartner with opposite quantum statistics. If supersymmetry is exact, the contributions to vacuum energy from particles and their superpartners would cancel exactly, leaving zero vacuum energy. But supersymmetry must be broken at low energies since superpartners have not been observed, and the breaking typically reintroduces large contributions to the vacuum energy. String theory offers another potential resolution by proposing that the fundamental building blocks of reality are not point particles, but extended strings. In string theory, the divergences that plague point particle theories are automatically regulated by the finite size of strings, potentially providing a finite answer for the vacuum energy. But string theory predictions for the vacuum energy remain model-dependent and difficult to calculate reliably. The landscape of string theory vacua compounds this difficulty by suggesting that there may be 10 to the power of 500 or more ways to compactify the extra dimensions required by string theory. Each compactification corresponds to a different low-energy physics with different particle masses, force strengths, and vacuum energy. This vast landscape makes it difficult to extract unique predictions from string theory. Anthropic reasoning suggests that we observe the particular vacuum we do because it's compatible with the existence of observers like ourselves. In a multiverse containing all possible string vacua, only a tiny fraction would have sufficiently small vacuum energy to allow galaxy formation and stellar evolution. The apparent fine-tuning of the cosmological constant might be a selection effect rather than a fundamental property of physics, but anthropic explanations remain controversial because they seem to give up on the traditional scientific goal of predicting observed phenomena from fundamental principles. If the fundamental constants of nature are environmental accidents in a vast multiverse, then physics might be unable to explain why these constants take their observed values. Loop quantum gravity approaches the problem differently by proposing that space-time itself has a discrete structure at the Planck scale. In this framework, the infinite number of vacuum fluctuation modes is automatically cut off by the granular structure of space, potentially providing a natural resolution to the vacuum energy problem. The discrete structure of space-time in loop quantum gravity leads to specific predictions about the quantum geometry of space. Area and volume become quantized, with minimum possible values determined by the Planck length and Planck area. These predictions might be testable through precision measurements of gravitational effects or cosmological observations, but loop quantum gravity faces its own challenges in making contact with standard particle physics and cosmology. The theory naturally describes pure gravity without matter, and incorporating the standard model of particle physics requires additional assumptions about how matter couples to the quantum geometry. The problem of quantum gravity extends beyond technical difficulties to fundamental conceptual issues. General relativity treats space-time as a dynamical field that can curve and propagate, while quantum mechanics typically assumes a fixed background space-time in which quantum fields evolve. Combining these perspectives requires understanding how space-time itself can be quantized. The Wheeler-DeWitt equation, which applies the principles of quantum mechanics to the gravitational field, treats the geometry of space-time as a quantum operator subject to the Schrödinger equation. But this equation faces severe technical difficulties, including the problem of time. If space-time geometry is quantized, what parameter serves as time for the quantum evolution? Various approaches to the problem of time have been proposed, including the idea that time emerges from correlations between different parts of the quantum gravitational state. In this view, time is not a fundamental parameter, but an emergent property of quantum entanglement between gravitational and matter degrees of freedom. But these approaches remain largely formal, with few concrete predictions that can be tested experimentally. The energy scales associated with quantum gravity are typically far beyond what can be achieved in terrestrial laboratories, making direct tests of quantum gravitational phenomena extremely difficult. However, cosmological observations might provide indirect tests of quantum gravity through their effects on the early universe. If quantum gravitational effects modified the dynamics of cosmic inflation, they might leave observable signatures in the cosmic microwave background radiation or the distribution of galaxies. The cosmic microwave background, measured with extraordinary precision by satellites like UMAP and Planck, provides a snapshot of the universe when it was only 380,000 years old. The tiny temperature fluctuations observed in this radiation are thought to originate from quantum fluctuations during inflation that were stretched to cosmological scales by exponential expansion. If quantum gravity modifies the behavior of these primordial fluctuations, it might show up as deviations from the standard predictions of inflation. Searches for such signatures have so far found results consistent with the simplest inflationary models, but future observations might detect subtle effects of quantum gravity on cosmological scales. Gravitational wave astronomy, inaugurated by LIGO's detection of merging black holes, provides another window for testing fundamental physics. The propagation of gravitational waves through spacetime probes the structure of geometry itself, potentially revealing quantum corrections to Einstein's equations. The LIGO detectors have achieved sensitivity levels where quantum effects become important for their operation. The shot noise that limits sensitivity at high frequencies arises from the discrete nature of photons in the laser beams used for detection. This quantum noise sets fundamental limits on the precision with which space-time curvature can be measured. Future gravitational wave detectors, including space-based missions like LISA and third-generation ground-based detectors, will achieve even greater sensitivity and might detect quantum effects in the gravitational waves themselves. If quantum gravity predicts modifications to the propagation of gravitational waves, these effects might become observable in precision measurements of wave arrival times and polarizations. But even with these advanced detectors, testing quantum gravity remains challenging because the effects are expected to be extremely small. The Planck scale, where quantum gravitational effects become important, is 17 orders of magnitude smaller than the scales probed by current particle accelerators and 20 orders of magnitude smaller than atomic nuclei. This vast separation of scales means that quantum gravitational effects are typically suppressed by enormous factors when they appear in low-energy phenomena. Observable effects require either extreme conditions like black hole formation and evaporation, or extraordinarily precise measurements that push the boundaries of current technology. Black holes provide natural laboratories for testing quantum gravity because they involve both strong gravitational fields and quantum mechanics in essential ways. Hawking radiation, the thermal emission from black holes, arises from quantum effects in curved spacetime and provides one of the few quantum gravitational phenomena that can be calculated reliably. The temperature of Hawking radiation is inversely proportional to the black hole mass, making stellar mass black holes extremely cold with temperatures far below the cosmic microwave background. But primordial black holes, if they exist, could have much higher temperatures and might be detectable through their gamma-ray emission. The evaporation of black holes through Hawking radiation leads to the information paradox, the question of whether information that falls into a black hole is destroyed when the black hole evaporates. This paradox pits the principles of quantum mechanics, which insist that information must be conserved against general relativity, which suggests that information behind the event horizon cannot escape. Recent developments in holographic duality suggest that the information paradox might be resolved through quantum entanglement between the black hole interior and its Hawking radiation. If the black hole interior is quantum mechanically equivalent to highly entangled radiation, then information is preserved, but in a form that's extremely difficult to decode. The holographic principle suggests that our three-dimensional reality might be information encoded on a two-dimensional boundary, like an image projected from a hologram. The ADS-CFT correspondence demonstrates this mathematically, showing exact equivalence between quantum gravity theories and simpler boundary field theories. If our universe is holographic, then space and time might emerge from quantum information processing rather than being fundamental. This connects to quantum error correction, where codes that protect information from decoherence appear naturally in black hole physics. The universe might literally be a quantum error correcting system, with physical laws emerging from computational constraints rather than geometric principles. Testing these ideas requires quantum computers capable of simulating holographic systems, a task needing thousands of qubits operating coherently. Current quantum computers use various approaches: superconducting circuits that operate quickly but require extreme cold, trapped ions with long coherence but slower speeds, photonic systems that work at room temperature but struggle with interactions, neutral atoms that could scale massively, and topological qubits that would be naturally error-resistant but remain largely theoretical. Each approach faces trade-offs between speed, reliability, and scalability. Progress continues rapidly, with billions invested globally, though practical quantum advantage for important problems remains years away. Quantum computing raises profound questions about reality itself. If quantum computers can solve classically impossible problems by exploiting superposition and entanglement, are they accessing parallel universe resources as many worlds suggests, or simply using physical phenomena classical physics cannot describe? The quantum internet will connect these machines using entangled communication, enabling perfectly secure cryptography and distributed computation. But quantum information cannot be copied or amplified like classical data, making quantum networks inherently fragile. Current systems work over hundreds of kilometers. Global networks require extending this to thousands while preserving entanglement quality. As quantum technology advances, it continues revealing new aspects of quantum mechanics while raising fresh puzzles about reality's nature. The theory that began with Planck's quantum surprises us with new implications more than a century later. In the quiet hours when consciousness fades into dreams, perhaps we enter quantum reality directly, where impossible events occur routinely, multiple possibilities coexist, and boundaries between self and world become fluid. Sleep might provide our closest access to quantum consciousness, where classical logic gives way to superposition and the measurement problem dissolves. The quantum theory that breaks reality invites us to question everything about existence and consciousness. In revealing quantum foundations, we've discovered the universe is far more mysterious and interconnected than classical physics imagined.